Okay, hi everyone. I think we should get started. Thank you all for coming. My name is Alex Buckley. I work in the Java platform group at Oracle. This is Modular Development with JDK 9. JDK 9 is here, and there's a lot in it. Some of the features are performance improvements, such as compact strings. Some are tooling improvements, like the search box in Javadoc and the new JShell tool. Quick show of hands. Who's tried JShell? A lot of hands. Right answer. Other features are updates to existing features, such as support for Unicode 8. But the main feature, and the one that's taken many years to come to fruition, is the module system. The module system is a big deal because it enables modular development all the way down. The Java language and the Java virtual machine understand modules very deeply, so that the applications you write and the libraries you consume, and even the JDK itself, can all be developed and tested and packaged and deployed as modules with clear APIs and well-protected internals. Making everyone play by the same modular rules has great benefits for reliability, maintainability, and security, as we'll see in the rest of this talk. So with the theme of modules all the way down in mind, this talk has three parts. The first part explains how modules are a long overdue building block in the structure of application code. The second part is about how applications and the libraries they depend on can migrate to modules. More broadly, it's about how you can mix modular code and non-modular code. And the third part is about the structure of the modular JDK, including some of the compatibility issues that arise from it. So, programming in the large. In object-oriented programming, the basic unit of reuse is traditionally the class. Java has wonderful mechanisms for promoting reuse of a class: inheritance for reusing behavior, interfaces for reusing abstractions, separate compilation, dynamic linking, and access control all the way down to the level of individual fields and methods. And we've had nested classes since 1997, so it should be possible, setting up a little straw man here, should be possible for a single top-level class to encapsulate a vast amount of functionality. And so it seems that an application could be a single package containing a few very rich classes, all sharing data via fields and methods accessible within the package, and where a handful of public classes form the entry points or the API of the application. Right? Not really. How many people work on a code base that consists of one package? No hands. Right answer. 2 packages? 3? 5? How many people work on a code base just within your company that's about 10 packages? 20? No, okay, finally, okay, you're awake, good, okay. There are some hands. On the order of 50 packages? Wow, 100? We're going to break the record. The record is 400. Order of 200 packages. If you know, it's actually quite impressive if you even know the number. Wow, more than 200 packages. That's actually terrifying. So, the point that has been extremely well made, thank you very much, is that no one's application consists of just a handful of packages anymore. Even the smallest microservice wouldn't be expected to fit into a single package. Programs are packages, not classes. Unfortunately, the Java language kind of gives up once your program is bigger than a package. Just imagine how difficult it is to control reuse within a large code base like the 217 official packages in JDK 8. The only way to share code between packages is with the public modifier, but then the code is shared with everyone. It's not surprising that package friendship, in one form or another, has been requested many times over the years. A package, in other words, is a great way to organize classes, but most people wish there was a way to organize packages too. Modules let you do that. A module is a set of packages designed for reuse. This is a long overdue building block in the Java language. In effect, modules record the structure of your program so that the packages you want to be reused can be reused, while the packages you don't want to be reused can't be reused. A program built of modules will be more reliable than a program built from a loose set of packages in jar files that can access each other freely and that expose too many APIs to the outside world with public. In other words, in JDK 9, programs are modules. Here's a module that everyone will soon be familiar with, Java Base. Java Base is the foundation of every Java program, like Java Lang Object is the root of every class. In blue are the packages of Java Base intended for use by code outside the module. These are its exported packages. In red are the packages internal to Java Base. They can be used by code inside the module, but not by code outside the module. These are its concealed packages. A module is declared in a new kind of file called modulinfo.java. That gives the name of the module and its exported packages. And so by exporting the Java Lang package, it means that the public classes of Java Lang are accessible from outside this Java Base module. A package that is not explicitly exported, such as ComSun crypto provider, is concealed. Its public classes are not accessible outside Java Base. This is the first feature of modules in JDK 9, strong encapsulation. A module isn't really just a set of packages, it's a set of exported packages and concealed packages. The public classes of exported packages are accessible outside the module. The public classes of concealed packages are not accessible outside the module. This means that access control is more powerful in JDK 9 than in JDK 8. In JDK 9, you can arrange for public classes to be accessible to everyone, or accessible only to other classes in the same module, or accessible to classes in the same module and a limited set of friend modules. So if you're looking at PUB-LIC on a class declaration, it no longer means that everyone can access the class. Access depends on whether the class's module exports the class's package. Since Java Base is a module, let's reuse it with a module of our own. Here's a class in the package ComExample hello. Let's declare a module for it, hello.world at the bottom. There's a modulinfo.java file, and for sake of argument, let's export the ComExample hello package with the exports directive. Now you're probably wondering how the hello world module knows that it has a package called ComExample hello. After all, nothing in the package seems to point to the hello world module. It's up to tooling to decide during development which module each package belongs to. In practice, the IDE will take care of it. You create a modular Java application, you're asked the name of the module, and then every package you create will be part of that module. If you run javac by hand, then javac figures out which module each package is in. That's why modulinfo.java is at the same level as the com directory in src. The benefit of relying on tooling is that it's really easy to place an existing package in a module and immediately give that package the benefit of strong encapsulation. We don't want each and every class to have to opt in to strong encapsulation by declaring the module it belongs to. That would invite errors, such as classes in the same package attempting to join different modules. That's a big no-no for reasons I'll mention later. One more thing, the say hello class imports the Java Lang package. Where is that package imported from? Now you might say, the answer is obviously Java base, because you told me a minute ago that the Java base module exports the Java lang package. You're right. But in general, how does a compiler know that? Should it search the file system looking for modules which export the imported package? What if multiple modules export the imported package? If we intend to reuse the Java base module, we should document that fact. Actually, since we're writing a module ourselves, we must document that fact. This is the second feature of modules in JDK 9, reliable dependencies. A module isn't just a set of packages. It's a set of packages that reuses the packages exported by other modules. So the Hello World module specifies that it reuses the Java base module with a requires directive in modulinfo.java. This means that code in the Hello World module can import any of the packages exported by Java base. What happens if code in the Hello World module tries to import any of the packages concealed by Java base, such as Sun security provider, in red? Here's an example of some code that did that, Glassfish 4.1. It, at the time of slide manufacture, didn't run on JDK 9 because the JVM throws an illegal access error. The error message is, you can read it because it's big, class ComSun Enterprise Security Provider Policy Wrapper in module, unnamed module, don't worry about that, cannot access class Sun Security Provider Policy file in module Java base. Now, a glance at the OpenJDK repository shows that the policy file class is declared public in the Sun Security Provider package. But because that package is not exported by Java base, policy file is only accessible from code in Java base itself. And to be clear, in JDK 9, the Glassfish code cannot access the public policy file class at compile time or runtime. It's exactly like trying to access a package private class from outside the package. Javac gives an error, the VM throws an illegal access error. So, sorry Glassfish, you'll need to find a supported API, not a sun.star API. I'd like to return to the modulinfo.java file that declares the Hello World module. It's really important to understand that a module exports packages but requires modules. The reason is due to an old software engineering principle. The unit of reuse is the unit of release. This principle is about separation of concerns. You reuse someone's code not by copy-pasting it into your own source tree, but by depending in some way on the black box artifact released by someone else. Now, in the Java ecosystem, there's no question that the unit of release is the jar file. That doesn't change with modules. A jar file, helloworld.jar, simply carries the modulinfo.class file produced from modulinfo.java alongside ordinary class files. We call this a modular jar. So when someone releases a modular jar for the Hello World module, it's reused by someone else writing requires Hello World in their own modulinfo.java. The reuser benefits from an explicit coherent API consisting of precisely the exported packages. The releaser benefits from strong encapsulation of concealed packages inside the module which support the API. Even if there's high coupling inside a module, there's loose coupling between modules, another good software engineering principle. Okay, so you're requiring Java base from your Hello World module, and you've built a modular jar for your Hello World module. Where do you put it? JDK 9 looks for modules in the system image and on the module path. The system image is in the JDK installation directory. It contains Java base and a few dozen core modules, Java SQL, Java XML, and so on. The module path is set on the command line, like the class path, except that the module path usually points to directories containing modular jars rather than to the jars themselves. So Java -p mods specifies that modular jars are to be found in the mods directory, and -m hello world specifies the module to run. The key point about modules requiring each other is that the module system can check the requirements and validate that a modular application is sound. Once the compiler or runtime has found that initial module, -m hello world, in the system image or on the module path, the module system performs then a process called resolution. Resolution means inspecting its requires directives and finding those required modules in the system image or on the module path, then recursively resolving them. We're building a graph whose nodes are modules and whose edges are the requires relation. And to be clear, in JDK 9, we do this at compile time and runtime. If resolution succeeds, you get 3 guarantees. First, nothing is missing. Every module that is required is available. Okay, pretty obvious, but a big improvement over the class path where you won't discover missing jars until later. Second, modules don't depend on each other in a cycle. Cyclic dependencies lead to code that is hard to maintain, and we're taking the opportunity to prohibit them in modules from day one of JDK 9. Now, some of you are thinking, well, you may be thinking many things at this point, but some of you are thinking, this is just dependency management. Doesn't Maven do this? Bear in mind that Maven only works at compile time, and the resolution process I'm describing works at runtime as well. But more importantly, resolution does something that no build tool can do, because resolution has the exports available as well as the requires. In particular, resolution checks that if code in one module imports a package, then the package is exported from exactly one other module. This means there are no split packages. A split package is what happens when 2 jars on the class path contain the same package, and you load some classes from one jar and other classes from the other jar. Split packages are a huge failing of the class path mechanism because they lead to very difficult to debug scenarios. Thanks to resolution, where every package is effectively single-sourced, they're impossible in a modular application, which is great for long-term maintenance. In fact, this is really what we mean by reliable dependencies. The dependencies in a graph of modules are reliable when each module can access only one version of a package at a time. The guarantee of no split packages is a big deal for performance as well. Because we know precisely which module exports which package, there's no need to scan every module in the system image and on the module path when trying to load a class. Contrast that with how you load classes from the class path. Here's the class path for Hadoop. The compiler or runtime has to do a linear search through 110 jar files whenever a new class is needed. Now, of course, the implementation can speed things up by caching the classes it found when it wasn't looking for them. But there's still that nasty half here, half there problem of packages split across multiple jars. In fact, if you think about it, the class path is crazy. With 110 jars, there are over 12,000 possible interactions between classes in different jars, each one starting a linear search. The class path is the ultimate in erasure. Whatever you know about the structure of your application, the class path throws it away and connects everything to everything else. With modules, you're telling resolution what you know about the structure of your application, and it uses that information to provide both safety and performance at compile time and runtime. The prohibition of split packages in modules has an impact on application design as well. One reason that a package, I should do a survey at this point, who here is aware in their application of a package being split across multiple jars? A reasonable number of hands. Not everyone, but a significant minority. So one reason that, you might have done that, was to allow different parts of an application to share package private code while allowing those different parts to evolve independently. Now those jars cannot be turned into modules because they would all be exporting the same package. However, the module system has a better way to structure the application as a whole than splitting a package. Let me set up this scenario in a bit more detail. Assume all of this takes place in a pre-JDK 9 world. On the left, the application has an API intended to be globally accessible. It's the public API interface in package P. The application also has at the bottom some helper code which creates or assists implementations of the API without being accessible to users of the application. It's the p.helper package. Then on the right, the application has implementations of the API, again intended to be not user accessible. Those are classes X and Y, which live in different jar files. So in order for the helper code and the implementations to work together and share code, they need to be in the same package. The implementations are package private so that user code can't access them. A helper class, foo helper, on the left, API helper, sorry, is package private as well. It could be public, but then it will be accessible to users, and again, we don't really want that. So with this setup, where you're sort of overloading a package, there's a bunch of problems. For one thing, you've got to make sure that the implementations don't tread on each other's toes. There can't be any class name overlaps between the implementations since they all contribute to the same package, p.helper, despite living in different jar files. A second problem is that you cannot make effective use of sub-packages. As the implementations grow larger, it would be natural for them to introduce sub-packages. But sub-packages cannot access the package private code in the p.helper package, so you need a public class in that package to be a backdoor for sub-packages in the implementations, and then of course anyone in the world could use that backdoor as well. A third problem is that anyone can make a jar with classes in this p.helper package and start using the helper code in the API jar, or start to rely on the details of the X and Y implementations in their jars. So like I said, what's really going on here when you have a split package is that the package being split, p.helper, gets overloaded. It started life as a simple namespace for code that helps the API, but now it finds itself being the unnatural home for all kinds of things. But what was the developer meant to do? In JDK 8, the only structuring mechanisms were classes, interfaces, and packages. Splitting the package across jar files was seen as acceptable, but you can see that it has a host of downsides. In JDK 9, the structuring mechanisms are classes, interfaces, packages, and modules. Modules take the strain of encapsulation and concealment so that packages can focus solely on being namespaces that are meaningful to the developer. So here's the same application developed as modules. Let's turn api.jar into a modular jar file by adding a module declaration. The module called API exports the package P with the API interface to everyone, and it exports the helper package, p.helper, to its friend modules, impl1 and impl2. Now that second exports directive is called a qualified export. Any module in the world can say requires API to depend on the API module and can access the package P. But only the friend modules can access the package p.helper. Now I'm not showing the module declarations for those friend modules, impl1 jar and impl2 jar. They'll obviously require the API module in order to access the API interface that they implement. The friend modules won't export anything, and they can organize their concealed packages and sub-packages as they wish. Now, the p.helper package is not overloaded with implementation classes from multiple jars. The naming of packages is much clearer throughout all 3 jars, and more implementations can be added smoothly without treading on another implementation's toes. In effect, modules make packages as cheap as classes and then control the reuse of packages very precisely. So part 1, a module is a set of packages designed for reuse. Modules offer strong encapsulation and reliable dependencies. Module-aware tooling is a big part of modular development. Let's talk now about how to take an existing application and migrate it to modules. Since it's impossible to modularize the Java ecosystem all at once, we're going to be living with a combination of modular code, modular jars on the class path, on the module path, and non-modular code, traditional jars on the class path, for a while. That's fine, and JDK 9 can help ease that migration. That's what this section is about. So we'll start with a simple application that we want to migrate from the class path. At heart, a typical Java application has 3 layers. At the top are your application jars, might be one or more of these. At the bottom is the JDK, and in the middle there's a bunch of library jars downloaded from the internet and thrown on the class path. Now, I've hinted that we've turned the JDK into modules. In this section, green boxes will represent modules. You've already seen the Java base module, and you won't be surprised to learn that there are also modules for logging, database access, and XML processing, Java logging, Java SQL, Java XML, and so on. But our application isn't modularized, nor are any of the libraries. Should we modularize our application? It's up to you. You could just run it on the class path like you always did. The class path still exists in JDK 9. The class path still exists in JDK 9. Some people think it's going away. It hasn't. But we modularized the JDK for a reason: to improve security through strong encapsulation and stability through reliable dependencies. Applications might want to benefit from this, just like the JDK does. So let's look at how we might turn this application into modules. Let's imagine it's 2 jars with main code in myapp.jar and helper code in mylib.jar. Let's also imagine that the soup of library jars is limited to Jackson, the JSON processing library. Jackson comes as 3 jars: core, data bind, and annotations, and of course the green modular JDK at the bottom. This is how we'd run the application today. We've got to set up the lib directory to include our application jars and our library jars and point the class path at them, then run using the Java launcher. One of the things we gain by modularizing is not having to list dependencies on the command line or in a script. So let's look at one scenario for migrating this application top down. Here we first modularize our application jars without modularizing the library jars. In general, if you depend on third-party libraries, you are depending on them to modularize. And while we can make it easy for such libraries to modularize, generally you have to wait for them to do it, and no one can force them. So it may well be that some of the libraries you depend on are not modularized yet. That's okay. Now, for the application jars, the obvious thing to do is turn them one-to-one into modular jars, where each jar file has a module.info.class file. This is not always possible, especially if your jars have cyclic dependencies, but let's go with it for now. If we're going to turn each application jar into a modular jar, we'll need to write a module declaration in modulinfo.java. Recall that a module declaration gives a name, a list of required modules, and a list of exported packages. The names are easy, myapp and mylib. We don't yet know what each module depends on. We could make a manual analysis of the source or the class files, but there's an easier way, which is the JDEPS tool. JDEPS scans class files or jar files and tells you what code from other jar files they depend on. JDEPS actually came with JDK 8, and there's an improved version in JDK 9. And while it's not perfect, it's a pretty good start for figuring out what you depend on. So we'll run JDEPs on the application jars with the Jackson libraries on the class path. We see that myapp.jar depends on 2 of the Jackson jars, which remember are not modularized yet, and of course on mylib.jar, plus myapp.jar depends on the JDK modules, Javabase and JavaSQL. JDEPs can tell that based on the APIs that myapp is consuming. Mylib.jar depends only on Javabase, so that's nice and simple. And now we have what we need to write our module declarations. So we'll start with mylib, the smaller library. We know it depends on Javabase. We can write requires Javabase, though we don't actually have to. It's always put in for you by the compiler, since every Java program ultimately relies on Java-lang object, which is in Javabase. Now, from the JDEPs run, we know that myapp.jar depends on mylib. If we'd run JDEPs with more options, we'd have seen that, in particular, myapp.jar needs the package com myapp.util in mylib. Now, we could write exports com myapp.util, semicolon, in the module declaration to allow anyone to access the package. But if we're sure that no one except myapp will need access, we can use a qualified export to maximize the encapsulation. And that's what we've done here. Let's turn to the module declaration for myapp. It requires mylib and those 2 JDK modules. And we know it's going to use Jackson, but we're not yet sure how to write the requires directives for Jackson yet, because Jackson isn't modularized. Does that mean that we have to turn, by we I mean you, have to turn Jackson into modules before you can modularize myapp? That would be unfortunate, since I assume no one in this room controls the Jackson jar files. Maybe there is a Jackson committer in this room. Is there a Jackson committer in this room? No, okay. If only there was some way, until that person shows up, for the Jackson jar files to somehow become modules automatically. We don't know what the dependencies and exports would be of those modules, but we have a pretty good idea of what the names would be. They'd be the same names basically as the jar files, jackson.core, jackson.databind, and jackson.annotations. And if we could do that, we could finish writing the module declaration for myapp. Happy faces. We'd have a lovely module graph that a quality IDE will visualize for you, with myapp depending on mylib and Jackson Core and Jackson Databind, and on Javabase and JavaSQL. The good news is we can do this with automatic modules. An automatic module is a module whose declaration is inferred by the module system from a jar on the module path. So if you have library jars that are not modular jars, you can still put them on the module path, and the module system will turn them into modules automatically. In effect, this means that yesterday's jars are already today's modules. Once automatic modules spring into existence for Jackson Core, Databind, and annotations, the module graph looks quite different. The automatic modules with the red border basically say requires for everything. That is, they require each other and all the modules in the image and all of your modules as well. And they export all of their packages. Now, that may well not be the set of requires and exports that the Jackson maintainers would write by hand, but the way the automatic module is inferred is really a feature, not a bug, because it emulates the behavior of the jars when they were on the class path. So in other words, we're providing the maximum possible compatibility surface for code in jar files when they're placed on the module path. And actually, it's better than when everything was a jar on the class path. If you look carefully, there is no arrow from mylib to myapp. So there is no danger of code in mylib accidentally reaching into myapp's internals. On the class path, code in mylib.jar could access code in myapp.jar quite easily, or in fact in any of the Jackson libraries it's not meant to be using, without even knowing it. And that accidental access is what causes maintenance headaches down the road. So that was a quick section. Each application jar is usually a good candidate to be a module. Each library jar will modularize at its own pace, that is to say, become a modular jar with a module info.class file. But automatic modules means that you never have to wait for the weakest link, for that one library that's not been modularized yet. You can move it from the class path to the module path, start requiring it, and very often it will work. For the third part, I'd like to turn our attention to the modular JDK. 20 years ago, the Java platform was small, just a few hundred classes, and the organization of the JDK wasn't a problem. But every year, the platform grew bigger, and now it's tens of thousands of classes. The JDK is huge, and worse, it's monolithic. Now, in reality, the Java platform is not one thing. It's more like 25 separate frameworks, including the Swing UI framework, the crypto framework, a scripting framework, multiple XML processing frameworks, and so on. There's no reason these separate frameworks have to be tightly coupled in one download. In fact, it's an impediment in developing the JDK. The overly tight and sometimes accidental coupling raises development and testing costs, which turns into slower platform evolution. Plus, the larger the surface of your platform, the more difficult it is to secure. And it's an impediment to a lot of users, both those who want to run applications on smaller devices and those who want to run more instances of their applications on large systems. Even if you only wanted a part of the JDK, you had to take all of it. That all changes in JDK 9. We've taken the modular JDK and broken it up into a few dozen modules. Some of these are part of the Java SE specification, some are just part of the JDK implementation. This is a graph of the Java SE modules. At the bottom, there's Java Base, which everything depends on and which depends on nothing itself. We've broken out the various frameworks into their own modules, instrumentation, logging, XML, scripting, desktop, etc., which you can require or not require as your needs dictate. There's a Java SE module which has no actual code in it, but just has dependencies so that you can say requires Java SE and be guaranteed to have all of these modules available. Now, it's worth mentioning that merely finding these module boundaries, which might be obvious in hindsight, was a tremendous engineering effort. You'll find in your own code that decoupling a monolith is harder than building a loosely coupled system from the beginning. The good news going forward is that the discipline imposed by modules will prevent all of us from accidentally recreating a monolith. I'd like to quickly review the expectations of compatibility from this modular JDK 9. First, there are various technologies from Java EE that ship in the JDK as well as in app servers. The list of Java EE modules in JDK 9, I didn't have them on the prior slide because it makes it messy, but the list of EE modules in JDK 9 includes JAX-WS, JAX-B, Common Annotations, and Corba. Now, these modules are deprecated in JDK 9 and will be removed in a future release. To prepare for removal, these modules, these 6 modules, are disabled by default in JDK 9. If you're running code on the class path that uses any of their APIs, then you can use the add modules flag on the command line to enable them. But please understand this is a stopgap. Going forward, you need to obtain standalone versions of the Java EE technologies. Now, standalone versions are available on Maven Central today. For pointers, you can see the removal JEP that we've just submitted. So there's the URL. At some conferences, the first row is photographers who enthusiastically take photos of every slide with a URL in, but not here. The second thing about compatibility in JDK 9 is that a lot of tools and libraries try to access parts of the JDK that are meant for internal use only. Now, unfortunately, it'll take a while for tool and library developers to move away from this practice. So JDK 9 temporarily allows access to JDK internals, but prints a warning when it happens. Now, there's a command line flag to avoid these warnings, so please check with tool and library developers about how to deploy on JDK 9 if you see such a warning. Finally, there are miscellaneous changes in JDK 9 that are unrelated to modules, but might affect code that ran on JDK 8. Notably, code that assumes the Java version string begins with 1 dot, or assumes that the JDK lives in a file called rt.jar, will fail on JDK 9. Again, please check with tool and library developers about which versions are needed to run on JDK 9. You can't always assume that old versions of tools and libraries will run on JDK 9 unchanged. So the modular JDK is modules all the way down. JDK internals are accessible temporarily in JDK 9, and you may need to upgrade tools and versions to their JDK 9 aware versions. So to step all the way back, a module is a set of packages designed for reuse. Automatic modules assist with migration to modules, and again, you may need to upgrade your tools and libraries to their JDK 9 aware versions. Now, there's a huge amount in the module system that I haven't had time to talk about, and you're going to ask me questions about in the remaining 4 minutes. You can encapsulate resources in a module, not just classes. You can express optional dependencies by programming with services. You can build custom system images with the JLink tool, so you can drop Corba right now if you wish. And you can spin up multiple versions of a module with the Module Layer API. If you're interested in this, I recommend 2 books. The first is Java 9 Modularity, out last month. It's a pragmatic walkthrough of the entire module system and the modular JDK. And the other book is Java Application Architecture from 2012. It's a principled look at constructing modular applications, and it has very good advice that applies whether or not you use the module system in JDK 9. So JDK 9 is on java.net today. If you're a library maintainer, please run JDEPs to see which JDK internals you rely on. And again, you can do this right now with JDEPs on JDK 8. Everything you ever wanted to know about the module system is discussed in JEP 261. I cannot emphasize enough how much valuable information is in that JEP. There's also JEP 260, which identifies the JDK internal classes that are exposed in JDK 9, exported for the time being. JEP 223, which defines the new version strings, and JEP 220, which describes the changes to the structure of the JDK, including how rt.jar has gone away. And finally, JEP 200 gives an overview of the JDK modules themselves, but if you've read JEP 261, there won't be any surprises in that. And with that, thank you very much. So we have 2.5 minutes for questions. Front row, enthusiastic. The question is about module-aware WAR files, and to pull on that piece of string, what is the situation with modules in EE4J? Please ask them. Next question.
So you can export to a module. So I'm wondering, how is that not a cyclic dependency?
The question is, you can export to a friend module, to a number of friend modules. And how is that not a cyclic dependency? That is an excellent question. I really ought to have a slide about it. The point is, if one module requires another, and then that other guy exports back to his friends, I mean, I've just drawn, and it's like, when I say no cyclic dependencies, I mean no cycles of requires directives. So A requiring B, requiring C, requiring D, oops, requires A, that's no good. But the qualified exports, they're not part of that relationship, because you may never actually access any of the exported types. It's much easier to use this than to explain it, to be honest. Okay. Mario has a question.
I'm trying to modularize the library, the framework on which I work. And I'm finding it difficult to find which package should be part of the public API and which package should. Because yes, we have a limited set of packages and we say to our user, to our customer, you should only use it that one. But then we found that some customers use a different one and some other customers. It's very difficult to mark a boundary. Do you have some suggestion for this situation? Because I talked with another friend who is the Jetty maintainer, is exactly the same situation. So I believe it's quite common.
When taking I'm not going to say a legacy code base because that would be rude. I don't mean that at all. When you take an existing code base that was designed with far too much being public because things were trying to access each other's different packages were trying to share information between themselves, and so things had to be public. And maybe those public things were then, posted to Stack Overflow. We have the same pain. The end result being that the modules you declare, you have to export more packages than you would ideally have thought were your supported API. All modules really do is expose the usage scenarios that people want. So modules are not a silver bullet. If it turns out that your module has 100 packages and you need to export all of them because that's just the structure of the API, then to some extent I can't help you, right? And any change that I suggest you might make, the next question will be, but that's binary incompatible. And again, there's not a lot the module system can do about that. It's simply reflecting your intention as the library owner. It's really the contract between you as the library owner and consumers of that library. So I'm actually waiting for someone to say, I have a cyclic dependency, what can I do? The answer is work. You have to work. There's nothing, well, I suppose you could not make modules out of these things, but there's no keyword, there's no command line flag to make all of the problems go away. If someone in your framework or someone in Jetty is accessing public types that you regard as unsupported, and of course the JDK has plenty of them, then you have to educate your users, which is why the illegal reflective access warning message that the JDK gives when you reflect over internals has very specific advice. Please report this illegal access to the maintainer of. Okay, I think there's another question.
What happens if you have an external library which in turn has split packages?
The question is, what happens if you depend on a library that is perhaps perfectly pure and can be put on the module path, but when it was on the class path, it needed other things on the class path. So the good news is you can leave those old things on the class path. So here's an interesting thing. Your module is going to require this library, which I'm going to assume you're putting on the module path as an automatic module. So you can write in your module requires Jackson. Great. Your application cannot see anything on the class path. In other words, your dependencies are reliable. The only things you can see are what you require. But one thing I obviously went through very fast is that automatic modules, such as Jackson Core, etc., they can see what's on the class path. Maximum possible compatibility surface. So you can leave whatever stuff you had on the class path with all of its messy split packages, you can frankly leave them there forever. And the automatic modules provide a buffer or a barrier against that messy world. One more question I think we have. Oh, time's up, so ask this in negative time, please. The question is the exports directive powerful enough to say something like exports p.star or p.star star? The answer is, by design, no, it is not, because the purpose of the module declaration, and if you browse the module.info.java files of the JDK modules, you'll see what I mean by this. A very clear list of exports with no wildcards and nothing clever going on, just a flat list, is very helpful to immediately read and understand the supported API of a module. You would also get into things like, if you were to say export p.star or export p.star, but also exports p.q to a friend, now you have a clash, because exports p.star is going to everyone, and exports p.q is only going to a friend. So you'd have then that would be you'd have to figure that out, and there'd have to be errors to deal with that, and extra analysis, blah blah blah. I think we are finally out of time. Again, thank you very much.